Hello there, Physics 30. We are on to EMR Chapter 13, Lesson 7. Holy man, we're getting through this. So I should start with by saying alrighty then. Okay, so here we go. We're finished here, last lesson. We're going to skip this. We're going to skip this altogether. We're not going to worry about it. It's not something I'm going to test you on. It's kind of an extension of the curriculum anyways. It's kind of to help you graphical analysis. So if you're interested in it, you want to know, feel free to ask me, but otherwise we're just going to move on. So we're going to jump into interference, right? So we talked about interference in physics 20. That's a superposition where two waves are on top of each other. Okay, one key thing that you should note is that interference only works for waves. Okay, it's only for waves. Particles can't be on top of each other, right? Particles can't be in superposition is what it's called. Okay, they can't be in superposition, which means they're in the same position. All right, but waves can. All right, we have two types. We have constructive interference and destructive interference, and this is a pretty simple concept as far as physics 20 went. You guys had a pretty good understanding of this. I'm not concerned. So what's important though is that if it comes down to light or electromagnetic radiation in any kind of general form, interference results in increase in brightness or a decrease in brightness. Okay, so we're going to get bright spots and dark spots because of interference, and it's a very interesting thing. Okay, so we've interference. We're going to talk about things that are generally we're talking about monochromatic light. Okay, and that's for the same frequency and therefore the same colors. Monochromatic means just a red light or just a blue light or just a yellow light. Okay, these are essentially what lasers are. Okay, and the light also needs to be coherent, which means that it's basically in phase, right? So its crests and troughs are all kind of in phase versus incoherent, where it's crests and troughs, right? So there's a crest and trough there at the same time. Those are not in phase, okay? So what we want is we want things that are in phase together, right? And that's going to get us monochromatic light, okay? So that's kind of the idea of lasers. If the laser is incoherent, the phases are random, and that's kind of our everyday lights. You don't really notice the interference; it just kind of happens. Lasers are very inefficient. Less than 1% of electrical energy is converted into light. However, the laser beam is easy to direct; it doesn't spread over long distances. So they really like this idea. Okay, lasers allow us to take a lot of different colors of light or frequencies of light and bring them together into a single frequency and direct it over a long distance, which is great for experiments. It's an excellent idea. It also is interesting how it creates heat and doesn't create heat, and how things it leads us to all sorts of different experiments. Yeah, and so lasers are a useful tool, but they're not super efficient. All right. This is one thing. If you ever looked at like a soap bubble or like kind of oil on top of water, like clear oil, or anything like that, you notice this little bit of discoloration, right? Where it kind of goes a little bit different colors, like reds and greens and blues show up. Okay, also the rainbow. Now, some might think that that's similar to when we pass something through a prism, right? So when we pass something through a prism, right, we send light through a prism, it diffracts and ends up giving us all the different types of light coming out. So this is white, and then you kind of get a red all the way to blue, right, green in the middle. Okay, and that's a prism, but this is actually different, right? This film or this little thin layer, what we're actually seeing is interference, and so we're seeing interference, and so this is this is kind of basically when light comes in and part of the light reflects on the first part and part of it reflects on the second part, and they overlap or superposition on each other. We're going to get kind of where we have these wavelengths are going to constructively or destructively interfere. So this is not diffraction of light. Okay, this is the superposition and constructive and destructive interference, right? And so where you see the blue is where two blues are in phase. They're lined up together. Right, where you see red is where two reds are in phase and lined up together, and everything else is kind of canceling out through destructive. So what you see is where the constructive interference is happening. Okay, and this is when you're blowing bubbles, right? Blowing bubbles, you see this kind of color scheme. Okay, so we're gonna talk about diffraction. So as waves travel through an opening, they always bend or diffract. Okay, so there's two things we're talking about. light and it's a wave, right? If I have an opening and I shoot particles through it, right? Those particles are just going to keep going straight. Really, the opening does nothing, okay? But what waves do is they diffract, right? So they basically are going to bend around the opening, right? They're going to go or bend around the opening, okay? And so basically this proves that light is a wave, all right? This is the main way that Young did prove that light is a wave, because when you shine light through a gap, it doesn't just turn into a laser beam. It doesn't turn into a single line. It diffracts. It bends around, right? This is why if you were to have a wall and you were to put a wall in kind of a wave pool, right? Those waves would come in, but they would, as they went through this gap, you couldn't just stand here and the water would be perfectly calm. It doesn't work like that, right? These waves interfere and they move through each other and they actually diffract through an opening, right? So they actually cover that whole area. This is kind of another example of waves coming through a gap, okay? They spread out. All right, so you guys can actually click on this. There's a whole bunch of things. Take 10 or 15 minutes and just test all the different things you can. There's light, there's water, there's sound, there's 2 slits or 1 slit. There's a whole bunch of different ways you can see. You can change it. Okay, this should work on your Chromebook. It should be no problem. Please go ahead that. So what was interesting though with this experiment, and pause the video and go do that now, right? In order to observe the diffraction, the light had to be in phase. Okay, so we had to actually create a light in phase, except we can't just send a laser through it, right? We had to send light somewhat like this, right? A big, basically a barrier of light at this wall, okay? And then what we get is we get this idea that it's going to go through there and it's going to create this kind of diffraction grating. That's kind of called, it's basically diffraction pattern, right? And that's where we're going to get bright and dark spots. And you'll see that when you play with this video or play with this thing, right? And that diffraction, that dark and bright, we don't see that in everyday light because the angles are tiny. The angles we get are tiny. And the difference between a bright and dark spot, we're talking about micrometers. So we don't see that in everyday life. But if you set up an experiment, it's actually quite easy to see. Okay. So Young decided that he's going to do the double slit experiment. Okay, this is probably one of the one experiments that they're actually going to. You would see in the diploma. You would see me test on it lots, and you'd have to know quite a bit about this experiment and understand it, because again, this is the number one way that they proved definitively that light is a wave. Now there was ideas that light was a wave, but this proves definitively that light is a wave. But then on top of that, it also proves that it's also a way to measure light. We can measure wavelength. We can actually measure things. Okay, and that's important in physics. Is we really like to measure all sorts of things, right? We talk about, this idea that we Newton discovered gravity, right? Well, he didn't actually discover it. It's always been there, but Newton decided. But what really made Newton the idea, like it's not like the guys like Galileo didn't understand that if you drop something it fell. He understood that, right? Everyone understood that. Right, but what made Newton kind of the father of gravity is that he actually was able to put numbers on it and recreate kind of experiments that work, and measurable experiments, right? So same idea with Young's double slit experiment. They had a pretty good idea that light was a wave, right? But they couldn't really effectively measure it. They knew it had interference patterns, but they still weren't like super sure. Then we have this, okay? Okay, and so you can watch, you can kind of see this when you do it with that previous little applet there. All right, and basically what it is it's 2 slits, and we're going to send light at it, and we're going to see the light interfere with each other. But then we're going to put a screen, and then in the screen, what we're going to see is bright and dark spots. Okay, so Young's double slit experiment is basically we send light at this, and we have 2 slits, right? We have 2 slits, so this is the light coming in, very in phase, okay, and it's going to go through 2 slits, and what it's going to do is it's going to have constructive and destructive interference. Okay, constructive interference is bright. Destructive interference is dark. Okay, okay, so that's kind of important. And what we get this bright, dark, bright, dark, bright, dark pattern, right? And it keeps getting dark. And what happens is the bright is really bright, and the darks are quite dark. And then they get less bright, and darker, darker, darker. And so it's hard to see with the human eye. a lot unless they set the diffraction quite right. Okay, but with basically, since waves experience diffraction interference, this experiment is solid proof that light travels as a wave. Okay, and so we're going to get the central bright fringe is midway between the two slits because the path length of the path lengths for light from the slits are equal. Since the light is monochromatic, then constructive interference occurs, the region of gaze appears bright. So basically we have a bright, dark, bright, dark. And what we're going to basically call this is going to be a node or an antinode, right? Okay. Sorry, multiple wavelengths produce the bright regions. Bright regions are antinodes, all right? Bright regions are antinodes. And the dark fringes are nodes. We can use those, but the best way to do this is talk about, instead of saying nodes and non-nodes, we're going to call it order number. All right, so we're going to do bright, dark, okay, order number here. All right, order number basically means we're going to start at the center being 0. Now, I could label it down here, but I'm just going to do it up here, okay, just so it's a little bit easier, is we're going to call the center 0. So this is 0, okay? This is 0 because it's the central bright. Okay, there's always a bright at the center, so the central bright. And then what we're going to do is we're just going to count the brights in each direction. So 1, 2, 1, and 2. Okay, and we're going to call those are the whole numbers. So those are the brights in the whole number order. Okay, and what that means is that in between, right, each dark would then be a half. So this would be 0.5. This would be 1.5. Right, this one here would be 0.5, and this one here would be 1.5. All right, so basically what you're going to have a way to count these, right? So how far from this bright region to this bright region? Well, it'd be an order of 4. N would be 4, right? So you go 1, 2, 3, 4, right? But you can also count it like this. How far from the first dark to the second bright? Well, it's 1.5, all right? So if we go down here, and again, I'm going to come back to this equation. Okay, so if we consider this, we have all these different letters here. We have A, B, C, D, E, right? So we have A, B, C, D, and E, right? So we have the whole number. So if I look there, the central one, which has B labeled, would be the 0, right? A is a dark, so we know it's a half. And it's this closest half, so it's 0.5, right? And what you can do is you can say, well, it's the first dark, and then just subtract a half, right? The third dark, you would just subtract a half, so it would be 2.5, right? C would be a 1. Okay, C would be a 1. What about D? Well, D would be a 2, and E would be considered a 3, right? If I went halfway between D and E, it would be a 2.5, right? So just kind of keep that in mind. All right, so this is the important part of Young's double slit experiment, is that you can actually like measure things and it all works out mathematically, and that's just wonderful. We're all happy, okay? And so we have two equations. The first equation is this one. All right, lambda equals d sine theta over n, okay? Where lambda is the light length in meters, okay? The distance between the slits in meters, so that's the distance between the slits. All right, the angle from the center to the fringe in question, right? So that's the angle from this central fringe. Let's say it wanted fringe 3. Well, the angle between fringe 3 and the central fringe, right? If it wanted fringe 2, it would be the angle between fringe 2 and the central fringe. Okay, so this is good for measuring angles between the fringes to the center. This one measures from the fringe to the center always. All right, and then n is the order number of the fringe in question, right? So if I'm going to go from example, from fringe 3 to 0, then n would be 3, right? If I'm going to go from 2 to 0, then n would be 2. If I'm going to go from 2.5 to 0, then n would be 2.5. It's just how far from the center as in the order number, okay? In this equation. So one thing to note is that these are measured in meters. Light is almost always given to you in nanometers, all right, especially visible light. All right, it's going to give it to you in nanometers, so make sure you just take note of that and don't try and put in meters, and you'll get something crazy, some crazy numbers, crazy large numbers, right? We want small numbers here. Okay, the gap between these things is very small. All right, it's on your formula sheet, And I have an example here of it done. Okay, so determine the spacing of the rulings on interference grading if the third order maximum is observed to deviate from the central maximum using monochromatic light. Sorry, I think I said something wrong. Yeah, no, that's right. Yeah, determine the spacings of the rulings of interference grading. So that's one thing to take note of. Interference grading is basically, instead of just two slits, you have hundreds of slits. But this equation still is going to work if it has hundreds of slits or just two. Okay, and so that's what interference grading is. And basically what interference grading does is it does the same thing that two slits does, but it just does it more, left and right. You just get way more of this bright and dark region, and it kind of makes them brighter and darker, so it's easier to see. Basically what it is someone saw that you could do this with two, and you get bright and darks. And they say, well, I'll try three. And we got more brights and darks. And they're like, oh, what if we try it with 300? Right? And we get lots of brights and darks. Okay, and that's kind of the idea. So, determine the spacings of the rulings. And so we're basically determining the space between them. So we're looking for D. That's what's asking for. Right? And so I wrote down my information. I have my angle is 26 degrees. My wavelength is 548 nanometers. And N is 3, right? It's the third order maximum. Okay, another thing we'll call the bright spots is maximums. All right, so there's a bunch of different terms of bright spots, right? Okay, so one of them is maximum. All right, so we have that. So put that in the equation, right? And I solve backwards, and I get D equals 3.75 times 10 to the negative 6 meters apart, which is basically a thousandth of a millimeter, right? Well, almost 1,000th of a millimeter, right? Which is very small. So these slits have to be generally pretty close together in order to get this diffraction grading that you can actually observe it properly. All right, so that's that question. Okay, so here's the second equation. All right, and this is called Young's small angle approximation formula. All right, what that means is this formula is usually only good for angles less than 10 degrees, but I'm not going to ask you questions that are gonna this equation is going to wreck it. All right, so you wouldn't want to use this equation for the last question, right? You want to stick with equations that are less than 10 degrees. But yeah, and what you'll notice is this is one of the most interesting equations, because what you have is, if you look at all the units, it's all meters. These are all distances. These are all distances except for the end. The end doesn't have any units, right? The units do have to be meters. They do have to be consistent, though, right? So if this is measured in nanometers, then these and this also measure in nanometers. That's, again, one thing to watch. But what's difficult about this, especially, is the fact that we have this D, X, and L. All right, I use capital L if I can, right? But D, X, and L. So wavelength, we understand wavelength pretty easily. It's easy to separate from the rest of the measurements, but the rest of the measurements are distance between the slits, distance between the fringes, and the distance of the double slit to the screen. Okay, and so we have this distance here, the distance that's here, and the distance here, right? And so there's a whole bunch of differences and that kind of stuff where you don't want to get this, you don't want to put this number in for this spot and this number in for this spot, right? They're all measured in meters, so they're easily mixed up. So this equation, I would say, is one of the equations that in physics 30 is easy to screw up, right? It's easy to screw up, and so you really have to take your time, practice it, and then work forward from it. Of course, it's on a formula sheet right there, and you guys can see that. Alrighty, so a green laser light has a wavelength of 532 nanometers and detected a pair of slits that is 1.8 meters from the screen. Okay, so the 532 nanometers, right? I wrote that down here in meters, and then I said the screen is 1.8 meters away, right? So the length between the screen is 1.8. Okay, the difference between the slits is 0.25. Okay, millimeters. All right, so I put 0.25 into millimeters. It's times 10 to the negative 3, again, meters. All right, what's the difference between the first and dark fringe? The first one maximum and the third bright fringe. Now, there is a couple different ways you can do it. You could solve for the third and then solve for the dark, solve for the or the bright and then the dark, and then subtract them to get the differences. Or what you can actually do is you can actually just take the n value and subtract them immediately. Okay, that n value is going to actually work if you subtract them immediately, and it's going to work. So what I have is I'm basically measuring how far from here to here, right? So I just drew my little pattern quickly, all right? and I have the center bright. So this is the center bright, this one. Okay, and I'm going to go from the first order minimum. Okay, again, minimum is being dark. And the third bright. So I've got one, two, three brights. And so I'm going to go from the first dark to the one third bright. So it's 3 minus 0.5. 3 minus, so we're going to use n. It's equal to 2.5. We're going to use Young's small angle approximation, right? Because we're assuming it's small angle since it gave us the length and it gave us the distance between the splits and all that stuff. And we're going to solve for x. Okay, x is the distance between the fringes. All right, again, see how that's confusing? Which one's the distance between the fringes? Which one's the distance between the slits? Which one's the distance from the screen? Okay. If you happen to accidentally mix up x and d, you'll actually still get the same answer. Okay, but we are going to then put it in the equation, solve for x using our algebra skills, and I'm going to simplify it to 9.6 millimeters, right? Okay, if I look at the numbers here, that makes sense. Right, it makes sense because the slits are 0.25 apart, right? The slits are 0.25 apart, which means that this would have to be at least more than that, but it's not going to be huge, right? We're not going to talk about, a big difference, but this is still less than a centimeter, right? And so it's kind of this idea, and it's 1.8 meters away, like that's 5 feet, right? That's 5 feet away. So, yeah, this kind of makes sense. Hope you guys are understanding this. If you're not, good luck, okay? The small angle approximation is mentioned in the Physics 30 diploma bulletin every year. I haven't seen it in myself in a diploma exam. I haven't heard of anyone actually seeing it. Basically, if they give you the numbers that you can use this equation, then you are generally allowed to use it. If the angle is over 10 degrees, you'd have to use SOHCAHTOA to try and figure it out, right? Which, of course, you could do. Anyways, but yeah, you could do anyways, but it's just easier as the equation goes. So, all right. So the next page, there's basically this understanding. I could go through all the algebra here and put this question in and stuff like that, and we get different answers for A and B, right? And the reason we get different answers is that for A, the angle is larger than you have to find the angle using trig, right? But yeah, like it just doesn't really show up that much in questions and stuff. And so they're different because this only works if the angle is 10 degrees or less. Okay, so this would be the correct answer for A. But basically just understand that at more than approximately 10 degrees, the equation B, the second equation, it just falls apart because of this sine theta being there. All right. So yeah, again, not something I'm going to test you guys on or put on quizzes or anything like that, but just keep that in mind. Okay. So I got this video here. It says, how far can Legolas see? Right. This is actually super cool. It talks about how light spreads out. It goes through diffraction over time and over space, right? The sun is brighter as you get closer to it, obviously. A light bulb is brighter as you get closer to it, but the farther away you get, the more spread out it is. And what that leads to is it actually limits our vision, right? And it's not so much what we can see. Like, you can still see objects and light coming off of objects, but as far as details go, right? And it talks about if you're looking at such a distance, then things at 100 meters away, anything that's smaller than a centimeter is going to look about the size of a centimeter, but be super blurry, right? And so your eyeballs are actually what limits your ability to see details. The curvature of the Earth limits your ability to see distance, but your eyeballs limit the ability to see details at a long distance. So check that out. It's kind of cool. Okay, and this is one of my favorite things. So basically what happened, and there's an article here, you can read through it and stuff. I clicked on it, the lights still work. And what this is basically a bunch of French physicists are arguing, I think it's the 1800s. Yeah, early 1800s. And they're basically like, okay, can someone figure out why light behaves the way it does? And basically one of the scientists, he went ahead and he said, well, light's actually a wave, you guys. And this guy named Poison, he mocked him. He said, that's ridiculous. That's utterly ridiculous. And so he said that by saying that's ridiculous, he then said, well, if light's a wave, then if you took a beam of light, so you took a light bulb, took a light bulb, and then you put a perfectly spherical object, and you sent waves at it from that light bulb, right? So this is, right, you sent waves at it. Okay, well, when the waves hit, you would have diffraction, and you would get this. So he was basically making fun of it and saying, I'm just gonna copy this for it. Okay, he was basically saying, well, since light's a particle, right? When it does this, when you shine the light, it's just gonna shine like this around this spherical object, right? But then he made fun of me. He said, well, I mean, it's ridiculous. What's going to happen is you're going to shine the light, and if it's a wave, it'll actually diffract around this. So it'll actually diffract around the sphere. And you'll actually get a bright spot on the edge of the sphere, right? You get a bright spot on the edge of the sphere, on the opposite side. So the light's here, and you'll actually get a bright spot right in the center of that sphere. And so a guy listening to this argument says, well, that's a perfect experiment. And so he actually sets up the experiment, and this Poison guy, who is making fun of him for being ridiculous, actually told this guy how to do the experiment. So he does the experiment, and he sees the bright spot, right? And you can see it here. That's a pretty good little picture of it. You actually see a bright spot. So if you shine light at a perfectly spherical object, and you make it super dark in a nice monochromatic light, right, you'll actually get a dark spot on the far, or a bright spot, sorry, on the far side. And that to me is one of the coolest things about physics, right? And so this was kind of the first idea, but again, you couldn't really, this was around the same time as, this was before Young's double slit experiment, but it begins to show that people had an idea that light was waves. They just couldn't measure it and prove it, and that was kind of the issue. So yeah, this is pretty cool. All right, so you got practice problems 30 to 35, and then no quiz, because, we don't do quizzes no more, but at least not closed book ones. You guys have those open book quizzes, which are basically just practice problems extended. So yeah, that's the end of this lesson.